Okay, welcome all in this new video. Today I will be talking about reverse recovery time because reverse recovery time of a PN junction diode. Okay, so why it is called reverse recovery time? Actually, this is a kind of recovery time. Recovery from what? Recovery from. So this is a recovery from previous stage to new stage. Generally, in case of switching, PN junction switching, when we switch a PN junction diode from, let's assume, forward bias to reverse bias or reverse bias to forward bias. Okay, so let's assume we are having a switch over here which can be connected from to this point or this point, and it is connected with some series resistance RS. Even if RS is not connected, PN junction have, apart from this body, a junction area, it has a neutral region. So this neutral region, ultimately it is a material, so it have some resistance. So this I can call as RS. Okay, combining both P side and N side, both, or this RS can be an external circuit. So let's assume this was already connected with the forward bias, and then it is being connected with reverse bias. Then in that case we will say that the diode is switching from forward bias to reverse bias. Okay, so at t is equal to t1, let's assume this one is done. So ultimately earlier it was forward bias of VA and then a reverse bias of VR. And if it is other way, then we will call that the switching is from reverse bias to forward bias in the other case. Okay, so let's assume that it was previously connected with VR and then it is connected to VA, then it will be a switching from reverse bias to forward bias. In both cases, some recovery time some recovery time is needed. Now, as I have discussed in depletion capacitance and transition capacitance, that diode capacitance, generally in reverse bias it is the depletion capacitance, C depletion, and in case of forward bias it has diffusion capacitance, which is like exponentially it increases. So this is your diffusion capacitance, C diffusion, which is equal to I forward divided by Vt into tau, because this IF is proportional to e to the power Va upon Vt, right? And that's why it is exponentially increasing. And of course, the stored charge, if you see, that is more in case of forward bias as compared to reverse bias, and that's why the recovery time for from reverse bias to forward bias is small. Okay, so recovery time for coming from reverse bias to forward bias is small. And so in general, in textbook also, you will find that people are not talking about any recovery time for reverse bias to forward bias. Generally, we talk about recovery time from forward bias to reverse bias because earlier, if the PN junction was forward bias, that means we were already having a very high capacitance in forward bias, and hence, because C was very high, this implies that uh, delta Q, the charge stored across the junction, that was quite high in case of forward bias junction, and hence coming from forward bias to reverse bias, that is needed, that we need to deal with a very high amount of charge that has to be transferred on the other side of the junction, so it takes time. So the recovery time is large or very big time, and that's why we generally, this is the bottleneck, this is the critical condition which we should address, and that's why in all books, textbook, in academic purpose or even for experimental practical purposes, people are dealing with this forward bias to reverse bias recovery time. If this one is okay, then of course this is a smaller one, so this will be taken care in case of switching. Okay, now I am coming to the point that if your transistor is forward bias, then it has to transit from forward bias to reverse bias. How much time will be required and what are the different charges which needs to be transferred from one side to other side? Okay, so let's assume there is a PN junction. Here you have P type, here you have N type, and of course in case of forward bias the junction will be quite thin. Let's assume this is the junction area. So in this case, this is XN, XP. And let's assume that this N type is doped with ND and P type with Na, accepted atoms per centimeter cube. Oops. So the majority carrier on the P side, that will be P is equal to Na. Likewise, majority carrier on the N side, that would be N is equal to Nd. Right. What will be the minority carriers on this P side? So N will be equal to Ni square divided by Na in case of uh, thermal equilibrium, not in powered bias. Okay, and the minority carriers in the N side, that is P, that will be equal to Ni square divided by Nd. Generally, we use subscript P for P side and N for N side. Okay, and we use subscript 0 for thermal equilibrium. This is the standard notation. So this will be the carrier distribution at around thermal equilibrium. However, because this is a forward bias junction, in forward bias we know that the PN junction, uh, the Fermi levels are not aligned, but they are separated by QVA. If VA is the forward bias, right? EFN and EFP, and hence the normal mass action NP is equal to Ni square, that is not valid in case of forward bias around the junction. Okay, here this Np will be more than Ni square. In fact, it is e to the power Va upon Kt. Sorry, Kt upon Q. So I should write it Vt. So Va is the forward bias divided by Vt. So Np value that exists in this junction region, that will be even greater. So what will be the P value over here? When the junction is biased with a forward bias VA, that will be P on the N side, that will be into N on the N side, that will be equal to Ni square into e to the power VA upon VT. You can write it as Pn is equal to Ni square upon, because this N is a majority carrier, so this is not going to change in case of small or low level injection. So in case of low level injection criteria, this N is not going to change, it will work as a buffer stage. Okay, so this is of the order of 10 to the power 16 or something, and this one is 10 to the power 4, like this. And that is quite high. So it will be simply, you can write it as ND, e to the power VA upon VT. Okay. So this charge over here, that is Pn at x is equal to Xn. Why this is actually quite high? Because more number of holes from the P side, they are diffusing on the N side in case of forward bias, and that's why the hole concentration will be quite high. Now as if we move further in the Cauchy neutral region of the N type material, recombination will happen, right? Because there is no electric field in this side, and hence now in this side the mass action law, that is Np is equal to Ni square, that will try to be maintained, and that's why there will be a lot of recombination, and because of that it will reduce exponentially as you go inside the N region. And what will be the time constant, or you can say that distance constant? That will be equal to the diffusion length. So e to the power minus x upon LP, diffusion length of hole in the material. Okay, so ideally it should be x minus xn. Anyway, so this is the expression for hole concentration in N side. A similar expression you can find for minority carriers in P side, right? And the excess charge on the P side, delta P. So what is the excess charge? So you will have to minus this P and naught, because this is the equilibrium condition. So that will be P and naught if you just subtract it. So this is nothing but P and naught. Okay. And that's why you can write it as P and naught e to the power VA upon VT minus 1 into e to the power minus x minus xn upon L. Now you would be thinking that why all these things are being explained when we have to learn the reverse recovery time. This is important if you want to quantify the things. Now this delta P, as you increase this VA total charge delta Q, that will be equal to integral of delta P integral from xn to infinity, and that you will find, of course, multiplied by cross section area. Okay, but I am counting it per unit area, cross section area. So that will be P n naught E into, so if you will integrate it, this is your V upon Vt minus 1, it is, or it should be out of the integral, an integral of this part that you will find as LP. So this is the total charge over there. Now suddenly if you have just a switch off the forward bias, then what will happen? Not only switched off the forward bias, but you have applied a reverse bias. Now you see the reverse bias condition. In case of reverse bias, this junction width has to be increased, right? So the junction width W, that will be quite large as compared to forward bias case. And also, if you use the same uh, concept, because now here VA is actually minus VA, so you will find that it will go like this. So this is the minority charge carriers in N and P side. Okay, because here in this case, this delta P, that will be equal to P n naught e to the power minus VR upon kT minus 1. Okay, so that will be the case. That's why it will go like this. Where this line is Pn0 is equal to Ni square divided by Nd. And this line is for Np naught is equal to Ni square divided by Ni. So we have to come from this stage to this stage. There are a lot of charges which are already there, and if you suddenly apply a reverse bias, the system will not move in a zero time from this to this, right? It will take some time. Now let me come to the exact scenario. What will happen? So earlier it was forward bias, and at t is equal to t1, let's assume the switch is thrown to the reverse bias condition. Earlier it was a forward bias of VA, now it is reverse bias of VR. Everything is happening. So this has happened at t is equal to T1. So earlier the applied voltage was plus VA, now the applied voltage is minus VR. So on time diagram, you have this is the applied bias to the circuit. Now as you have corrected this reverse bias, earlier the current in this circuit was a forward current, right? IF. Now suddenly, because a reverse bias has applied, but still we have a lot of excess carriers over here, right? So this is free charges. Of course, storage charge, it is called the storage charge. You can say that it is of stored charge on both sides. Now because the forward bias has stopped, so now this there will be no diffusion of extra carriers from this side. This has been blocked. Here we have a lot of electrons. Ultimately, it is a region where plenty of electrons are there, right? Plenty of electrons. N is equal to Nd. Earlier, because a lot of holes were actually being supplied, and that's why some holes were actually existing in this region also. But now, because this supply has removed, now these electrons will actually recombine with these holes, and it will start decreasing. At what rate? The hole recombination rate. And that is why these lines will be, with time, they will actually decrease. With time, it will decrease. Ultimately, it will follow the same line, NP0, sorry, PN0, right? So now that will become in the equilibrium stage when VA is equal to 0. But still, this is not the reverse bias. After that, we have to come to this stage, and that is why the current over here right now, that will be exactly decided by the reverse bias and external resistor, and it will be minus VR by R. So that is in blue color. I am just plotting this current. Why it will be constant? Any one of you? This current in reverse bias will be constant up to some time, because that would be decided by the external circuit. Okay. So this circuit, we will have a reverse current that will be equal to minus VR upon RS, because still during this time the junction is almost like it is having a lot of free charges, and junction is not in action right now. Okay, unless until all the charges are actually removed by recombination, then only the junction action will come into picture. Okay, still there is a lot of free charges, and hence it will be seen as a transparent. Okay, and voltage across it is still VA. Okay, if you plot the voltage across diode, that will still be plus VA. So that will be plus VA forward voltage, that is of the order of 0.5 volts. Till when? Till the time all the storage charges are removed. When all the charges are removed, that means the junction has come to its equilibrium of the normal condition, but still it is not reverse bias. After that, suddenly the junction potential, that will change, and of course, depending on the resistance R, actually the voltage will be uh, applied. This voltage will share some of the portion, and this resistor will share some of the applied reverse bias. After that, what will happen is that, because we have to come to this stage, and so once all the charges has been recombined, but still to come to a reverse bias of this plus on this side minus on this side up to approximately VR, what will happen? These charges will actually start depleting from the junction. Okay, so this will follow like this. As it will deplete from the normal stage, of course the bits will keep on increasing, and a negative charge will come on this side, a positive charge will come on this side, and finally we will get this reverse bias condition. So during this time, the current will be not constant now. Now it will actually try to regain its reverse saturation current. Okay, and that is why this is the IV characteristic of during the transition time. So up to this time, the storage charge is being recombined, right? But still, the voltage across the diode is equal to VF. Okay, once it is done, then actually VD will be equal to 0 volts. Okay, and during this time, that is called the uh, regain or gaining or attaining the reverse bias. That means the voltage across the diode that will tend to VR, because in case of reverse bias, now this current will become IS, which will be very small. So the voltage drop across this series resistance that will be very small, and hence all the voltage will drop across this. Okay, so let's assume the current over here that was IR. This time is called the storage time, T storage, and the total time when this current rises to 90% of the final current, or you can say that if the whole current was IR, then to reach up to 0.1 IR, that is your recovery time. That is how it is defined. So reverse recovery time, this TRR is equal to 2 T storage time and plus T, let's assume, to attain the transition uh, stage, that is a depletion width. Okay, now this storage time is approximately equal to tau p. In fact, it is equal to tau p ln if plus ir divided by ir. So that depends on what is the reverse voltage you have applied and what is the series resistance. Okay, one few more important things are over here. So to reduce the reverse recovery time, we need to reduce storage time, because in general this storage time plays a very vital role. How to do that? So what is T storage? Technically is equal to delta Q storage divided by, of course, what is the total current that is actually flowing, that is IR. Okay, that is flowing in the reverse direction. Now you can write it as VR divided by RS approximately, and hence to reduce this storage time you should reduce this RS. So series resistance should be reduced. So that is one option. Or You should reduce the reverse bias. That is another thing. Sorry, increase the reverse bias. Okay, but this is only for TR storage time. The another time factor, this one. Okay, from here to here, that will increase if you will increase the reverse bias. So this is technically not correct to achieve it. Okay. Another thing is reduce delta Q storage. The storage charge that can be reduced by two methods. If you see the whole story, what was that? The storage charge was this one, this area, right? Where this point was Pn0. Now this storage charge can be reduced if we reduce Pn naught. How to reduce Pn naught? Because Pn naught is equal to N square divided by Nd, right? So if we increase the doping concentration on one side, of course Pn naught will be reduced, right? And this at a given bias, this is Pn naught e to the power Va upon Vt minus 1, right? This value. And hence this will also decrease, so the whole area that will be reduced. Okay, so the new style will be something like this. Over here, like this. So the total area will be, the storage charge that will be reduced. So the number one option is increase one side doping too high. Okay. For example, you should have P plus N junction or P and N plus junction, something like that. One of the application is that Schottky diode. In case of Schottky diode, what we do is that we have a P-type semiconductor. On the other side, instead of N plus, we are having metal. Okay, so this is not a semiconductor, we have simply metal. So what happens is that the storage charge in this region, that will be no stored charge. Okay, a lot of electrons are over here, very high. So there is no holes over here on this side. Of course, and that's why the storage, the time that will be reduced to almost zero in case of Schottky diode. They are especially used in case of high frequency applications. Right. Also, if you reduce NP0, you will find that this charge, okay, that this time will also reduce. So that was one thing. Another thing is that because storage charge is totally dependent on recombination rate, right? So how fast it will be removed, that is depends on the recombination rate. So how to increase this recombination rate, or you can say that how to reduce this tau p. Tau p can be reduced by adding recombination centers in the semiconductor. Generally, if there are some deep defect levels inside between EC and EV, they work as a track state or recombination. Okay, and gold doping in a silicon. So in silicon, if you are having gold doping of the order of 10 to the power 14 per centimeter cube, they will create sufficient number of recombination centers where these electrons will fill over here, okay, and then from here they can actually combine with holes in the balance one. Anyway, you can say that, okay. So there are different analogies. If it was already filled, okay, you can say that holes are moving in this side or electrons are moving this side. So this recombination centers, they accelerate the recombination rate, okay. So another option is add recombination center. How you can do that? So gold doping. So I think I have completed this topic in more detail. So one application is Schottky diode application to reduce this recovery time. Even actually P plus N or N plus P junction that will work. But people are generally, because this is very easy, very right. The Schottky diode concept, that uh, is very easy to fabricate. Just on a silicon you should have very high metal content. Okay. Another option is like reducing the length of N or P side, right? So here you have this excessful distribution on the N side and P side. Sometimes people also do this, that they reduce this length of N. Okay, so the N region is not up to this point, but it will have only up to this point. So the excess charge, only this charge will be stored in the N region. Others are directly this metal. Others are directly, this is actually metal wire. So only this much charge has to be removed while switching from forward bias to reverse bias. This doesn't exist. Okay, so only this charge profile exists inside the N region. So another one more option is reduce N or P side length, especially low doping side. So L less than LP or LN. So this is another way of uh, reducing reverse recovery time. I hope that I have cleared it. If you have any questions, you can ask me in chat box. Thank you.